Good afternoon, everyone. Very good afternoon. So let's just wait for 10 minutes, okay? In the meantime, if anyone is having any doubts related to yesterday's session, you may ask your queries in the Q&A and in the chat, okay? If you have any doubts related to yesterday's session, please ask in the Q&A or chat, okay? So let's just wait for 10 minutes and we'll start the session. And today we'll discuss about random forest, KNN, and the classification metrics, okay? Okay, fine. Thank you. Sorry for the delay. So I hope everyone is here, right? So I'll just share my screen and we'll start the session, okay? Random forest we'll discuss first. Random forest or else bagging, you can see. Okay, we'll discuss about that first. Bagging or random forest, both means the same, okay? These are nothing but the ensemble machine learning techniques. We'll discuss about it. Just give me a minute, I'll share the PPT and we'll start the discussion. So today we are going to discuss about this random forest. Okay. Yesterday we are done with the decision tree, right? Remember the concepts in decision tree, everyone? Remember what is entropy, how to calculate the entropy, information gain. Remember, right? Everyone. Jagdish. I only remember few names, okay? So don't take me wrong, okay? Okay. Okay, fine. Got it. Okay. So now we'll be going into this random forest, okay? Yesterday mostly we have discussed about this information gain, Gini index, entropy, and what is the formula for it, pruning. Correct. We have discussed all these things, and regarding the limitation of the nodes also we have discussed that we can mention the maximum number of the maximum depth or the minimum samples for split and also the minimum samples for leaf also we have discussed, right? How many samples needs to be considered for each leaf or else each split, and how the root node is decided, how the information gain will play an impact, will play a role. Correct. So then now we'll be discussing about the random forest. Okay. Before discussing the random forest, in machine learning, we're having this technique called as ensemble techniques. Okay, ensemble machine learning techniques. Ensemble machine learning techniques is nothing but what we'll do exactly in this ensemble machine learning technique is we'll be having two concepts, bagging and boosting. Okay, bagging and boosting we'll be having. So bagging is nothing but bagging is also known as a random forest algorithm. Okay, now we are able to learn about this random forest. Okay, so for boosting, so boosting is, for boosting there is another name called as bootstrap also, or else we can say for boosting, ADA boost is an algorithm which is present. Okay, ADA boost, ADA boost. Okay, so let's learn about this bagging. Okay, if you understand bagging, you will understand boosting. You will understand boosting. Okay, it will be very simple. So let's see. So initially, what is that we are seeing over here? There were tree 1, 3, tree 2, 3, nth tree, and by considering all those three values or average output, we'll be doing the voting it is saying. So for now we don't know anything about bagging, right? But what we can see here, we can see that there is tree 1, tree 2, and 3 nth tree. We don't know what is the tree number, but it is an nth tree. So let's say tree 1 is giving the final leaf output as A, okay? In the decision tree, we'll be getting the tree outputs, right? What is the last classification, last leaf node? Based on the last leaf node, we'll be considering the class, right? Whether it belongs to which class. So tree 1 is saying you need to consider class A. In a column, we are having two classes, let's say A and B, okay? In a column class, we are having two classes, A and B. So coming into class, this tree 1 is saying the output is class A only. You need to consider class A. It is saying the last leaf node is class A, it is giving. And coming into tree 2, it is also saying the last leaf node is class A. Okay. Coming into nth tree, it is saying class B. And while doing the voting, what is happening over here? In the voting, what it is saying? Class A, right? It is saying class A. You need to consider class A, it is saying. So here, the thing is, in decision tree, we'll have only one tree, right? Decision tree we have only one tree, but in random forest we'll have the multiple trees. Okay, we'll deal with multiple decision trees. In decision tree we built only one tree, but in random forest we'll have multiple trees. Okay, multiple trees. But how the output will be considered? The output will be considered based on the voting. Voting in the sense we'll be doing average. Okay, we'll be doing average and we'll consider which leaf to consider. Okay, so just see here. Just see what exactly happening in bagging. So first we know bagging. What is bagging? Bagging is random forest algorithm. In the ensemble methods, we are having bagging and boosting. If someone asks you like what are these ensemble methods, like in an interview or else you're giving any viva, you can say that ensemble methods in machine learning, we are having these ensemble methods named bagging and boosting. Bagging, which is also known as the random forest algorithm, which can be used for both regression and the classification. Okay, random forest algorithm can be used for both regression and the classification problem. Here what happens is in the decision tree concept is applied over here, but the thing is in decision tree only one tree is built, but when coming into bagging, that is random forest algorithm, multiple trees are built, and how many trees needs to be built, that we will be deciding. Okay, that we will be deciding. And how these trees are built, based on the data. Okay, we'll be having a data, and that data will be deciding how many remember sampling, systematic sampling. Anyone know k-fold cross validation? K-fold, we'll be mentioning the folds. Okay, we'll be mentioning the fold over here. I'll just say the cross validation techniques also, don't worry. We'll mention the number of folds to consider over here. On the whole data set, we'll be mentioning the number of the folds. Mostly we'll be mentioning the fold in the format of odd number only. Let's say I'm having 100 values. Okay, 100 values data set I'm having. If I want to do the k-fold and perform this random forest algorithm, okay, build a random forest algorithm, initially I will be checking it. I'll be checking the data set if it is a regression or a classification. Then I will consider the algorithms. Like if I want to do random forest, then first I will be mentioning this k as 5 or 3, because the whole data set will be divided into 3. Okay, will be divided into, so if I say k equals to 3, Let me just write in the OneNote. I think if people are not getting anything, let me just write in OneNote. Okay? In between, you are having any doubts related to this implementation of random forest, we'll discuss. Okay, we'll discuss. Okay, we'll discuss. We will do this implementation part. We'll shift the implementation part to Saturday. Okay, we'll just complete all the theoretical part. We'll shift the implementation part to Saturday, or else on Friday we'll do the implementation. Okay, let me share the OneNote. OneNote. So in decision tree, what happens? Root node, just a minute. Root node, leaf node, branches, decision branches, or the decision nodes, right? This is decision tree, correct? Decision tree. But in random forest, what happens is random forest is also known as bagging, right? Bagging, which is nothing but the random forest model, okay? Random forest model. And this comes under the ensemble method, okay? Ensemble method. I'll just mention it in the chat, okay? Ensemble method, okay? Now, I had just told you how to explain what is random forest. So now I'll be explaining the workflow logic, okay? So random forest, how random forest exactly works. Now, decision tree means it will be building one tree. In random forest, what happens is initially we'll be considering the number of case, okay? Number of the case or else number of subs we want our data set to be divided into. If we mention k as 5, okay? If we mention k as 5 and we are having 1000 values, we are having 1000 values in our data set, okay? 1000 values in our data set. Now, this 1000 values will be divided into by 5, okay? By 5. By 5. So it will be like 200, right? So on each 200 values, a tree will be built, okay? A tree will be built. Okay, tree will be built. So, but what exactly happens here is this is a cross validation technique actually. I'm directly saying the cross validation technique. This cross validation technique is known as k-fold cross validation techniques. Let me just write here. I'll just write here. Okay. K-fold cross validation technique. Okay. K-fold cross validation. So, sorry. So this k-fold cross validation is nothing but it is a cross validation technique. So what exactly happens in this k-fold cross validation? In the k-fold cross validation, we will be defining k. Okay, we will be defining the k. K is nothing but the sets or the bins. And in this k-fold cross validation, how it will be present is k minus 1. Okay, k minus 1. So if I am considering k equals to 5, then it will be 4, right? The output will be 4. So now I am telling my data to be divided into 5. Okay, in the previous, here if you see, I'm having 1000 values at all, right? So if you see over here, the 1000 values for each k will have 200 values, right? Each k will have approx 200 values, correct? So but here what's happening, if k equals to 5, each k will be 200. So I want to consider each subset as 200, but I'm doing k minus 1. So what happens here is it will consider only 4 subsets. So on these 4 subsets, the random forest model will train. Okay, random forest model trains. Random forest model trains on 4 subsets. Okay, so what will happen to the remaining one subset? Because we are considering 5, right? Only k minus 1 is 4, right? So 1 will be remaining, right? That 1 will be coming under the test data. Okay, this one comes under the test data. Okay, test data. Okay, this is one kind of cross validation techniques. Okay, this is one kind of cross validation techniques. But why did I say about cross validation technique before saying the random forest? Because it will make to understand very easier for you to understand the random forest technique. So in the random forest, it's a combination of multiple decision tree, right? So it will consider the data and it will build the multiple decision tree. How it will consider the data? This is one kind of way to consider. Okay, if we divide the data by using the cross validation technique, we'll be having 4 subsets for the data and 1 subset for the test data. Then we can build the random forest model. So in a similar way, if you consider the whole 1000 values if you consider also, and if you divide this into 70 and 30, okay, 70 and 30, 70 and 30. So 30% is for test. Leave this, okay. Now 70% is for training data, right? So now what the random forest does is it will build multiple decision trees, okay. It will build multiple decision trees. Multiple decision trees it will be building, and based on the output of this, based on the output of this, based on the output of this, or else if say we are having another decision tree, and yeah, we are having these decision tree. We are having 5 decision trees, okay. 5 DTs in the random forest, okay. Random forest has built these 5 decision trees. Let's consider, okay. So now what happens is all these decision trees will be built parallelly, okay. All the decision trees will be built parallelly, okay. All the decision tree will be built parallelly, okay. Now what happens is it will be passing through each and every data point, okay. Don't worry, all the data points will be passing through each and every tree, and tree will be built. And how many trees, we'll be mentioning the number of trees also. So we'll be building these trees in the random forest model, and everything will be built parallelly, okay. Everything will be built parallelly. What happens is, now we'll consider one of the leaf node from here, leaf node from here, leaf node from here, leaf node from here, and leaf node from here. Okay, let's say I'm having a column yes or no, okay. Yes or no, okay. Either it could be 0 or 1, correct, or else 1 or 0. 1 or 0 we can see, okay. So from these decision trees, whatever the output I'm getting, if it is 0, 0, 1, 1, 1, okay, if it is like this, okay, then we'll be doing the average, okay. We'll consider the average over here. We'll consider the average. We'll consider the average, and then whatever the leaf node, highest leaf node average which we are getting, let's say we are getting 1 over here. So we'll consider that tree structure, okay. We'll consider that tree structure, and the model will be built based on that, based on this tree structure, okay. Model built based on this tree structure. Which tree structure? Whatever the any one of the tree structure it will be picking, and based on this, based on these values, as we are getting average this, so the model will be built based on this structure, okay. Is it clear how the random forest model is working? There is a disturbance from my side, okay. But did you understand how the random forest model is working, everyone? Simple, in a simple line we can say it builds multiple decision trees, and every tree is built parallelly, not one after the other. Everything will be happening one by one, like side by side the operations will be happening parallelly, the operations will happen. And from that we'll be considering the average voting, we'll consider the average voting, and then the decision tree is built, okay. The decision trees are built, and based on considering the average value, the random forest model will be considering, okay. So that is how the random forest algorithm works, okay. Random forest algorithm works. That is about bagging, okay. That is about bagging. So we'll just see over here. We'll just refer to the PPT now. Let me just share the PPT screen. If you're not understanding anything in between, please let me know, okay? Related to the topic which we're discussing, okay? Please let me know. Don't forget to inform me. Fine. Okay. Okay, fine. So even if you see here, tree 1, tree 2, and the nth tree, depending upon the, we'll be doing the voting. Voting is nothing but the average. We'll be doing the average. Then as per the voting, we are getting A, right? So that is how we'll be deciding the tree in the random forest. Okay. In the random forest, we can do both classification and regression. Okay. So now just move forward. We'll just move forward. Okay. So what it is saying, random forest is composed of collection of decision trees. Collection of decision trees, and trees are hierarchical structure where each internal node represents a feature. Each branch represents a decision based on the feature. Each leaf node represents the outcome of the class label. This we already know, right? These things we already know. What is the leaf node, what is the decision node, and what is the root node? We already know because we have seen in the decision trees. And random forest utilizes decision tree as its base learners. Okay, base learners. We'll have this base learners and weak learners concept also. And coming into this bootstrapping, what is this bootstrapping? What it is saying? Random forest employs a technique called bootstrapping to create multiple subsets of the original dataset. Bootstrapping involves randomly sampling data from the dataset with replacement to create new dataset of the same size as the original. Each decision tree in the random forest is trained on one of these bootstrapped dataset, introducing diversity among the trees. Understood, guys? Understood this bootstrapping method? Bootstrapping method. So what it is saying is, so I just told you, right? Whatever the data which we're having in the k-fold cross validation, if you consider whatever the data which we're having, it will consider the subsets, and on the subsets, each tree will be trained on the subset, right? So here you can say bootstrapping involves randomly sampling data points from the dataset without replacement to create new dataset. Okay, for each and every tree should be something different, right? Every tree should not be trained on the same data, right? So in order to make sure that the samples will be collected, I mean the random sampling will be happening on the dataset. Okay, random sampling will be happening, and from the dataset with replacement to create new dataset of the same size as the original. And each decision tree in the random forest is trained on one of these bootstrapped datasets, introducing the diversity among the trees. So what are the subsets which we are considering? Those random samples. Each tree will be trained on the samples number which we are considering, so that each tree will be different, and based on the average voting, we'll consider the random forest model. Okay, and the feature selection. How exactly random forest feature selection happens? So in addition to that bootstrapping also, what it is saying, it selects a subset of the features to consider when splitting the nodes in the decision trees. Okay, that this random feature selection helps to decorrelate, okay, decorrelate the trees and reduce the risk of overfitting. Remember pruning, guys? What does pruning do in decision tree? Pruning will reduce the complexity, right? So what here it is saying, random forest also randomly selects a subset of the features to consider when splitting the nodes. Okay, when splitting the nodes also, it will be considering the subset only, right? As we just discussed in the bootstrapping method, it will divide the things into subsets, and each subset will, on each subset a decision tree is built, right? So that it introduces the diversity among the trees. So in here, in the same way, when splitting the nodes also in the decision tree, the random feature selection helps to decorrelate the trees, and in return it reduces the risk of overfitting. Overfitting means the model will be trained on our data and will be getting a good accuracy, but when coming into testing, the model is completely failed to predict on the unseen data. Okay, and even also what happens, even if a model is being trained on the same data continuously, what happens, it will tend to predict those kind of pattern only. If you give a different pattern or it's a small change with a different value if you are giving, it will fail to give the output, right? It will not give a proper output. So that is what the overfitting is, okay? So what it is saying, the square root of the total number of features is used as the number of the features to consider at each split. So whatever the number of features we are considering, that number of the features square root will be considered at each split. At each split, it will be considering the square root of the total number of the features. Features means nothing but the columns. Like the outlook, rainy, those columns, okay? Relate to the example. I hope this random feature selection is important. It is important along with the bootstrapping method also. But in an overall point of view, that is how the random forest is working. Is it clear now? Clear, guys? Everyone? Okay. 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 So there is this boosting concept also in ensemble machine learning techniques. I'll just conclude that boosting. Okay. I'll just complete the boosting and we'll go into KNN. Okay. We'll go into KNN. Let's say boosting is present in this PPTs. Okay. Fine. Yeah. Voting or averaging. Yeah. During the prediction, what happens? It is saying random forest combines the prediction of all individual trees to make the final prediction. For classification task, it uses the majority voting mechanism, whereas tree votes for most common class labels among its prediction. It's again the most common class label as per the voting only. It's nothing but again the average, right? So for regression task, it averages the prediction of all the trees obtained by the final output. See this voting or averaging. Averaging we'll be doing for prediction for regression. Voting we'll be doing for classification. Okay, just remember that. Okay, but mostly it will be the same. Okay, and ensemble learning. Ensemble learning. Remember ensemble machine learning techniques I just told. Bagging and boosting. Bagging is nothing but random forest algorithm. In that we'll be having this bootstrap method. Okay. So what it is saying, random forest belongs to ensemble learning family of algorithms. Ensemble learning combines the multiple models to improve the predictive performance. Compared to any individual model, random forest leverages the wisdom of crowds by aggregating. Aggregating means adding the predictions of the multiple decision trees, resulting in the better generalization and robustness compared to single decision tree. What exactly is ensemble learning means? It is saying about the random forest and also what exactly happens in the random forest. It is saying just go through this ensemble learning and voting or average. Just go through these 2 points, guys. I'll just give it 2 minutes. Just go through these 2 points. Is it done, guys? Is it done? Okay, so this is pretty much about the ensemble learning. What is exactly the ensemble learning? What is the difference between voting and average? When to use voting and when to use average? And what happens in random forest? And what is the other name for random forest? Okay, this is it. So directly we are having KNN. So instead of diving into KNN, I just want to introduce you to the ADA boost. Okay, there is this ADA boost. Let me just share the screen for ADA boost. Second one, okay, I'll explain during the break. Okay, don't worry. Okay, so now we are going to discuss about boosting. Okay, just a minute. Okay, boosting we are going to discuss. What exactly is boosting? Boosting is also known as ADA boost. Okay, ADA boost. ADA boost. So ADA boost is an algorithm. Okay, ADA boost is an algorithm. So in ensemble learning, we are having bagging and boosting. Bagging is random forest. Boosting is ADA boost, which is another machine learning algorithm. But there is this difference between a bagging and boosting. In boosting, what happens is in boosting also we'll be having the trees. Okay, we'll also have the decision trees. Okay, here also we'll be doing that decision tree implementation only. But here we'll be having the concepts called weak learners, weighted voting. Okay, let me write here. First one is weak learners, learner. Okay, learners. Okay, learners, and then the weighted voting. Weighted voting we will say. Okay, weighted voting. So these weak learners and weighted voting are the key components or else the key concepts you need to know in the ADA boost. How the ADA boost algorithm is working. So initially what we'll be doing is we'll be initializing the uh, like we'll be what we'll be doing. We'll try to initialize the weights. Okay, initialize the weights for each sample in the data set and train that. Okay, so how it happens, I'll show you. So what exactly happens is this is the decision tree. So this is the decision tree which is built in the ADA boost. Just consider. Okay, is considered that is the decision tree built in the ADA boost. Okay, so now in this decision tree, we'll be having few of the values, right? We'll be having few of the values which the model is unable to learn on. Correct, which the model is unable to learn on. Correct, those parameters will be calling it as a weak learners. Okay, those parameters will call it as a weak learners. And sometimes few values will be left over, right? Sometimes few values will be left over. Okay, sometimes few values will be left over which have not been trained on the model. So now we'll be considering these leftover values or else the weak learner values, and based on this we'll be passing it to the other tree. Okay, these values will pass it to the other tree, and we'll make sure that this tree is training on these leftover or else the weak learner values. Okay, weak learners. What exactly weak learners is? Weak learner is nothing but each decision tree is a weak learner. Okay, and they're combined to create a strong predictive model. Let me write in the notepad. Okay, let's share the whole screen. Okay, notepad. Okay, so what are we discussing here? Boosting, right? In the boosting we are having ADA boost, and in this ADA boost, what exactly happens in ADA boost is we'll be having key concepts or key components. Key concept, we can say. One is weak learners. The second one is weighted. Okay. The second one is, first one is weak learners and the second one is weighted. What is weighted? Weighted voting. Okay. Weighted voting. So these are the key components. So what exactly happens in data boost? So initially on one tree and the samples which we are considering, okay, same here also we can use that K-1 cross-fold validation technique, okay. So in one tree, one subset of the samples will be considered, right, in this whole tree. So whatever the values which are left over to be trained on, or else whatever the predicted output which we are getting, whatever the wrong predicted values which we are getting from this whole tree. So let's say this tree is built, okay. Let's say one whole decision tree is built, okay. One whole decision tree is built, and whatever the outputs which were being predicted as wrong, whatever the outputs which were being predicted as wrong, these will be considering as a weak learners, okay. These will consider it as a weak learners, okay, and this will be passing them into another other decision tree along with the new subset. Here we will be having a new subset, right? This is a new subset value. This is a new subset, correct. On this subset, we got the values. We got the tree, and from the tree predictions, we can see few values are predicted wrongly, correct. Few values are predicted wrongly. That wrongly predicted values will be passed as a weak learners to this new model, okay, to this new model. So how the flow happens is decision tree output is weak learners, okay. Second subset, again, now what happens, we'll be having this decision tree model again, and the weak learners will go into decision tree along with the second subset. Here we are having the first subset decision tree. Whatever the output we are getting from the predictions, the wrong predictions, okay, the wrong predictions which we are getting from the decision tree, from the first subset of decision tree, whatever the wrong predictions which we are getting, that will be considered as weak learners, and that will be passed into the decision tree for the second subset, okay, decision tree of the second subset. So again, what happens in second subset of the decision tree? Again, the wrongly predicted values will be considered as weak learners. Okay, wrongly predicted values will consider as weak learners, and again that will be passed into third subset of decision tree along with these weak learners which are being predicted wrongly in the second subset, correct. So these subsets will be decided based on a k, right? So all these values will be passed, and finally a model will be built, okay. Finally a model will be built. So in boosting what happens is everything is sequential, okay. Sequential means one by one. First this will be happening, and then only we'll get the weak learners, right? Then only this will happen, and then we'll get another weak learner, right? Then only this will happen. So one by one, line by line, sequential, okay. In boosting the operations are sequential, and in bagging the operations are parallel, okay, parallel. And in boosting this mistrained or else incorrected predictions which we are getting, right, from the previous, that will be sent into the next subset, okay, next subset. So why exactly boosting will be helpful is to reduce the errors, correct. We are reducing the error. Boosting will help us to reduce the error or the bias, okay. We can say the bias also, BIAS, bias, okay. So this is pretty much about bagging and boosting, okay. This is how bagging and boosting algorithms work. Understood, everyone? Understood how the bagging and boosting is working? So in the next 1 hour, we'll discuss about the KNN algorithm. KNN algorithm, we can finish it off in like 10 to 15 minutes, okay. It's very simple, and it is a very lazy algorithm also. So we can finish it off, and then we'll go into the classification metrics of classification evaluation metrics we'll discuss. It's been a very long time we haven't discussed only. We'll discuss that, and if still the time is permitting, then we'll make sure that we are implementing the decision tree, and also the classification metrics. We'll try to implement the confusion matrix. All those things we'll do, okay. Fine. In the meantime, if anyone is having any doubts, please let me know. And also I have seen one query. That query was related to second one. Okay, someone was asking me to explain this ensemble learning. Okay, ensemble learning. Ensemble learning, what it is saying? It is a technique. Okay, ensemble learning are the machine learning techniques. What techniques? There were two kinds of techniques in the ensemble learning. They are random forest bagging and AdaBoost boosting. Okay, AdaBoost boosting process and the bagging process. So those are all the two techniques which will help us to make sure that we are reducing the error, okay, reducing the error, and then we are building a model. And how we are building the model? In random forest, we'll be using average routing, and in boosting also we'll be doing the same, but we'll be making sure that the error is being reduced. And in the bagging, we are doing the parallel operations. In the boosting, we are doing the sequential operations. That is what being told in the ensemble learning. Okay, that is what is being told in the ensemble learning. I hope it's clear, right? Ensemble learning, Vijay Kumar. Okay. Okay, while performing linear or logistic regression, the model is either overfitting or underfitting. So make sure whatever the data you're having is the clean data. Okay, you're pre-processing your data properly and you're performing scaling on the data. Okay, and also please make sure in the target variable the samples are almost the same. Okay, I mean the distribution of the samples are almost the same. If it is coming into classification, let's say 50% of the values to A and 50% of the values to B. This is like in this way, if there is a distribution, it's totally fine. But if you are having the distribution like 70% to class A, 30% to class B, in this case, the model will tend to give the biased response. Okay, so please make sure that you're not having these kind of data. Okay, please clean your data properly. In order to overcome that samples, you can do the sampling method. Okay, or sampling method, or the smooth process we can do. Is that clear, Jagdish? Okay. Okay, let me just check. Are there any other way queries? So someone was asking about the weighted voting. Okay. So weighted voting is nothing but, so from each subset of the decision tree, we'll be getting a weak learner's output, right? We'll be getting the wrongly predicted values, right? So each weak learner will get a weight. Okay. Each weak learner will be getting a weight. Okay. Each weak learner will be getting a weight. We'll be defining it, or else we'll be writing it in the alpha. Okay. Alpha value will be assigning to each weak learner, and based on its performance, the final prediction is being made, or else the weighted vote is calculated. Based on each alpha value, the final voting is calculated. Okay, that is nothing but the weighted voting. We'll be assigning the weights for them for each and every weak learner, and at the last, by calculating the voting, we will be deciding. Okay, so AdaBoost is nothing but it's a combination of multiple weak learners. Okay, multiple weak learners. By combining multiple weak learners, the boosting algorithms are built. Okay, is it clear, Aparna? Okay, fine. I see. Hopefully, everyone understood, right? So, Hemalata, what is your query exactly? Can you provide RE in the sense? I'm not getting. Okay, fine. Yeah. Thank you. So we'll just have a short break. Okay, we'll just have a short break. In the meantime, the attendance link will be updated in the Q and A. Okay, in the Q and A, in the chat, and in the YouTube also. The link will be updated. Okay. They are the distance metrics. Okay. They are the distance metric. Manhattan and the Euclidean are the distance metrics. While performing clustering, you'll be using this Manhattan or Euclidean distance. Okay. Based on the distance between the data points, a new data point, it will be assigned to a new data point. Okay. Yes, correct. It will convert all the weak learners. I mean, it will combine all the weak learners and it will form one strong learner. That strong learner will be our AdaBoost model. Okay, that is correct, Jagdish. But we need to use a terminology. Okay, while explaining weak learners, weighted voting. We need to know all these terminologies. If someone asks, could you explain what exactly the term is? Then we can go into this kind of explanation. Okay. Fine. We'll just take a break for 10 minutes. Okay. Be back here within 10 minutes. And in the meantime, please complete your attendance. Okay. Manoj, decision tree, yesterday we have done the explanation. Were you not present in the yesterday's session? If you're not present in the yesterday's session, that is totally fine. But in the last 10 minutes, we'll be explaining the decision tree. Okay. We'll try to cover the decision tree once again at last. Okay. Okay. So I hope everyone is here, right? Okay. So let me just share my screen. Now we'll be discussing about this KNN. Okay. KNN. Okay, fine. I'll just share my screen there. So what exactly is KNN? KNN is K nearest neighbors. So let's just we'll just go through these concepts, okay? And someone was asking me about this distance, Euclidean distance of Manhattan. In KNN, we can use the Euclidean distance, okay? In KNN, K nearest neighbors, we can use the Euclidean distance. So let me just give the difference, okay? Just look at this plot once. Just look at the plot. So we are having two different classes, right? Red and blue. Red and blue we are having. I'll just make the things fast. Red and blue we are having. So let's just say now we got a new data point, okay? Now we got a new data point. So just see this data point is near to which class? Red or blue? It is near to red, right? So it will be assigned to, so that is a new data point. And now based on the Euclidean distance formula, Euclidean distance formula is nothing but x2 minus x1 plus x2 minus x1 whole square plus y2 minus y1 whole square is the Euclidean distance formula. And the whole formula will be under root. So whatever the x1 and the y1 value of that new data point to that um, to this data point, okay? The x1 and the y1 value and the x2 and the y2 values will be considered for that new data point. Those values again for this data point, the distance between this and distance between from here to here and here to here we're considering, right? So x1, x2, y1, y2 we can consider, okay? Or else x1, y1, x2, y2 we can consider over here. And then we'll be calculating that based on the Euclidean distance, okay? And the formula is under root of x2 minus x1 plus y2 minus y1, okay? And similarly, then we will be deciding by calculating the Euclidean distance, then we'll be deciding do we need to assign this new data point to this class or this class, which is very near, okay? Which is very near, we'll be deciding and we'll be labeling this new data point under this red class, okay? As this is very near, by looking we can say. But if you are having points, then we need to do the Euclidean distance calculation, and then we'll be deciding if this new data point should be labeled as blue or red. Here we'll be labeling it as red, okay? So this is how the KNN works, okay? This is how exactly the KNN is working. And what is the what is the mathematics used over here? Euclidean distance. So one way to use. The other way is Manhattan distance. Manhattan distance is the mod will be applied and we'll be having the x and the y value only. The mod will be applied for it. So if you are applying the mod, we will not be getting the negative values, right? Okay. So we can use in the KNN, okay? The Euclidean distance will be and Minkowski. This is another formula, but mostly we'll be using Euclidean distance. But these two are also the distance formulas. Manhattan and Minkowski. Okay. See the new data point. So uh, we are doing a practical implementation. Let's say let's consider is equals to 5. K equals to 5 means 5. Okay. The 5 different subsets we are having in that case. Okay. See, what are these 5? If you're considering k equals to 5, the other 5 values over here, and this is a new data point. So for this new data point, we'll calc all the time, or else it is just right now. Were you able to hear me? Clear now? Is it clear now? I have connected. Clear now? Okay, I think it's clear now. So let me just share the screen of the PPT and I will explain that KNN once again. I hope no one understood. Okay. Okay. So now we are discussing this KNN, right? K nearest neighbor. I hope my screen is being shared. Okay. So in the KNN, the important things to remember is KNN is nothing but the nearest neighbor. K nearest neighbor. Okay. K nearest neighbor. So what exactly happens in KNN is, so initially whatever the new data point occurs, okay, so let's say we are working on a classification. Let's consider, okay, in regression also it will be the same. Okay, let's consider classification for now for simple understanding. So these two are the classes. Okay, these two are the classes, red and blue. Okay, red and blue. So now what happens, there will be a new data point, and new data point will be introduced for this particular whole whole data. Okay, let's say I'm having a new data point. So I'm predicting the model on the new data point, let's say. So now how the model will be assigning a label or to this new data point? It will be assigning the label to this new data point based on the distance calculation methods. It will calculate three kinds of distances, okay, distance matrix, that is Euclidean, Manhattan, and Minkowski. Okay, these three are the three distance formulas. Based on these formulas, we'll be considering the new data point and we'll be telling this new data point will either belong to this side or else this side. Okay, and how exactly are we saying, by considering what values we are saying it belongs to this side or this side? It will be depending based upon the k. Okay, let's consider k equals to 5. Okay, let's consider k equals to 5. So based on the new data point we'll be considering the nearest 5 values. Okay, we'll consider the nearby 5 values we'll consider, and on that nearby 5 values we'll be calculating the distance. Okay, we'll be calculating the distance. So let me just open the Microsoft OneNote. Okay, Okay, I hope this is being shared. So now we are discussing KNN, right? In KNN, the important thing is K only. KNN is K nearest neighbors, okay? K nearest neighbors. So let's say this is the plot and these are all the data points, okay? These are all the data points which we are having, okay? Now, let's say here we are having a new data point, okay? This one is the new data point, okay? New data point, okay? New data point we're having. And if you're saying K is equals to 5, okay? K equals to 5, it will consider the nearby 5 values, okay? It will consider the nearby 5 values. So what are the nearby 5 values? This is 1, 2, 3, 4, and this one could be 5, right? So it will consider nearby all these values, right? Nearby 5 values it will consider. And what happens? So that new data point we will have, new data point we will have what now? New data point and 5 other data points will be having, right? 5 other data points will be having. So now what happens is, in the Euclidean distance, okay? Euclidean distance formula is under root of x2 minus x1 whole square. See, that is the formula, right, for Euclidean distance. So now what happens is, what we are having 5 data points, one new data point, right? One new data point. So this one new data point will consider, and we will consider the one data point from here, one data point and one new data point, okay? One new data point. So between this we'll do the Euclidean distance, okay? We'll calculate the Euclidean distance. We'll draw a line, or else let's say in the plot that this is the existing data point, okay? Existing data point, and here we are having the new data point, okay? So now we'll calculate the distance between them, okay? Just consider a straight line over here. Consider a straight line. So x1 y1, x2 y2, and the calculations will be happening, okay? This is how the distance between two data points is determined, and we will get a value. Let's say that value is x. So we're having 5 data points, right? We're considering 5 data points, right? So let's say we are having 5 values, correct? We'll get each and every distance for each and every data point, right? So x1, x2, x3, x4, and x5 will have 5 distances for the new data point, right? 5 distance values for the new data point. Whichever is the minimum value, whichever is the lowest value, and what label it is, as per that only this data point will be allocated, okay? Let's say if this is a classification, now the nearest distance data point label is red, okay? Then this new data point will also be assigned as, the new data point label will also be assigned as label red, okay? Label red, okay? So this is how exactly it happens in KNN, okay? This is what exactly happens in KNN. Clear? Clear, guys? Clear, not clear? Let me know. It's clear, right, for everyone? What exactly happens in KNN? Okay, I'll just share the screen. Yeah, good question. Why that is called as a lazy learner? Good one, Harshni. Because whatever the nearest data point is available, it will be going and switching the teams. Correct. See, ఇప్పుడు like normal గా లేజీ లెర్నర్ ఎందుకంటామంటే ఏదైనా కొత్త డేటా పాయింట్ వచ్చింది అనుకో, నియరెస్ట్ గా ఎవరుంటే వాళ్ళలో వెళ్ళి కలిసిపోతుంది ఆ డేటా పాయింట్. సో అందుకని దాన్ని లేజీ లెర్నర్ అంటాం. K is our choice, but the thing is, mostly we'll be mentioning in between 3 to 5. Okay, only the odd numbers we'll consider. Okay. Okay, fine. Thank you. I hope everyone understood, right? No. What exactly happening is, in the training, it will be understanding what are all the data points, and it will be, so if you consider the classification, what exactly happening in the classification? It will be divided as per the labels, and the model will be learning on the labels. And whenever a new data point happens to come up, it will be assigned in the new data point the label, right? So that is what exactly is happening. Clear, Suraj? Okay, fine. We'll just see the workflow once. You'll get to understand. Okay, choose the number of the k of neighbors. How many neighbors you want to consider? Choose the number. Take the k nearest neighbors of the new point according to the Euclidean distance of Manhattan or else Minkowski. And among the k neighbors, count the number of the data points in each category. Okay. Assign the new data point to the category where you counted the most neighbors, and the model is ready. Okay. Let me just display that formula once. See, Minkowski formula is this. Okay, fine. So now we'll discuss this classification evaluation metrics. Okay. Okay, fine. Now we'll be discussing about this evaluation metrics. Okay, until now it's clear, I think. So we have covered until now. What are all the things we have covered, guys? Covered. Let me know in the Q&A, in the chat, what are all the things we have covered until now. We're done with all the pre-processing steps, and then we dived into the machine learning algorithms, linear regression, logistic regression, decision tree, random forest. I mean, the ensemble learning methods, bagging and boosting we covered, KNN we covered. Now, and evaluation metrics for regression we have covered. Now we are about to see the evaluation metrics for classification. Okay. Evaluation metrics for classification. So today, if you are done with evaluation metrics for classification, tomorrow we can start with Bayes theorem. Correct. So tomorrow we can directly start with unsupervised learning methods. Okay. Unsupervised learning methods will take 1 day. Not 1 day exactly. We can finish it off in 1.5 hour or 2 hours. Okay. And then we'll build on the model. And in the upcoming week, upcoming week, we'll completely focus on deep learning. Okay. Upcoming week, we'll focus on deep learning, and also we'll do a live coding for CNN. Okay. Live coding for CNN we'll do. Stacking. I didn't explain stacking model. What exactly what stacking are you referring? Okay. Sorry. I'm actually having a bad throat from a very long time. Okay. Okay, fine. So now the classification metrics. Is my screen visible? Let me just open OneNote directly. You'll understand it over there. I'm sharing screen again. Yeah. So I hope everyone is able to see the screen, right? This is called as confusion matrix. Okay. Confusion matrix. This table is known as a confusion matrix. Let me just write. Okay. Confusion matrix. Confusion matrix will be having the real and the predicted labels table. Okay. Real and the predicted labels table will be having in the confusion matrix. Real, we can also say it as actual. Okay. Real, we can call it as actual. And predicted labels, will be calling them as the predicted labels only. Okay. So we are seeing, what are the things we are seeing over here? The the real values, the predicted values, the positive and the negative. So in logistic regression, what happens in logistic regression, we'll have a sigmoid function. Based on that, the threshold will be getting either 0 or 1, right? We'll be getting either 0 or 1. Correct. So now, what exactly happens in this evaluation matrix is we'll be having four. Okay, mainly accuracy, precision, recall, F1 score. Okay, recall F1 score you will be having. So now initially to understand how those metrics are calculated, we need to know what exactly this confusion matrix table is. Okay, this table we will be calling it as confusion matrix table. Okay, so we'll be having the positive, negative, real values. Yes, draw on the real values, predictor labels, positive, negative, and negative we are having. Correct. So what it is saying, real labels means actually before going into the model, if it is positive and this is negative, and after going into the model, how it is being predicted, positive and negative. So that is how it is considering. Okay, that is how it is considering, and based on that we are doing the true false table. Okay, we're drawing this. So if the real label, if the in the real label, I mean in the original data set, if the value is positive, okay, let's say positive, let's consider a data set and the target variable is uh, like loan upload or not. Okay, loan upload or not, the values will be yes or no. Okay, if loan upload means yes, either yes or no will be the outcome, right? So here positive means you can say like it is approved, negative means not approved, just consider. Okay, positive approve, negative not approved. Okay, negative not approved. So now in the positive, real label is positive means loan approved, right? So in the predicted label also it is getting positive. Positive means even in the predictions also we are getting the correct output. That means the loan is approved only, correct? So we will be calling it as true positive. Okay, true positive. In the real label it is true, and also in the predicted label also it is positive. Then it is true positive. Okay, true positive. And also in the real label if it is negative, but in the predicted label if it is positive, then it will we'll be calling it as false positive. Okay, false positive. So what happens in the negative? I mean in this, what is happening over here, where our actual label is negative, but it is being predicted as positive. Okay, actual label is negative, but it is being predicted as positive. That we'll be calling it as false positive. Okay. And next, what are we having here? The actual label is positive, and it is also being predicted. It is being predicted as negative. So here the real labels we are having. Previously it was positive. Now the actual label is negative, and it is being also predicted as negative. Okay. So false negative. True negative is nothing but actually it is true, but it is being predicted as negative. Okay, actually is being true, but it is being predicted as negative. So this is what the true false table is. Okay, it will be a bit confusing. Try to understand this. Okay, try to understand this. The so if it is true negative means actual label is true, but it is being predicted as false. So it is true negative. Actually it is false, but it is being predicted as positive. So it is false positive. Okay. Let me just go through this once again. Okay. Okay. So we are having positive is you can consider like actual, real and predicted you can consider. Okay. Real is approved, predicted is not approved you may consider. So actually it is true, and it is also being predicted as true only, or else positive only. So it is true positive. Okay. Actually it is false. It is being predicted as positive. Actually the loan is not approved, but in the prediction it is saying that it is approved. So it is false positive. And coming into this false negative is nothing but actually it is false. Okay, it is not approved, and in the predicted label also we are getting the not approved only. So it is false negative. Okay, false negative. And then true negative, what it is saying, actually it is true. Okay, actually it is true, but in the prediction we are getting negative. Okay, prediction we are getting negative, so it is true negative. Understood this table? Understood this confusion matrix table? Is it being confusing? Are you people being confused, or else did you understand what is the real value by the predicted value? Okay, real by the predicted. So if the real value is true and the predicted value is also positive, it is true positive. Correct. I hope everyone understood, right? And if the real value is false and the predicted value is positive, then it is false positive. So actually, the loan is not approved over here, but in the predicted, it is saying loan is approved. So it is false positive, right? So remember this TP, FP, FN, and TN. Okay, remember this. Again, we will be discussing about this TP, FA when we are discussing about the evaluation matrix. Okay, this is a confusion matrix table. Okay, this is the confusion matrix table, and in the confusion matrix table only we will be having the same things again: TP, FP, TP, FP. What are the other things? FN and TN, right? So FN, TN. Okay. So based on these, we'll be calculating the evaluation metrics. Okay, we'll be calculating the evaluation metrics. So what are the evaluation metrics in classification? First one is accuracy. Okay, accuracy. Okay, accuracy. The second one is precision. Okay, precision. Precision. Okay, precision we can also call as specificity. Precision we can also call it as specificity. Ignore the writing, but understand the terms. Okay, precision, and also here we are having recall. Okay, so what exactly is recall? Recall is nothing but the sensitivity. Okay, sensitivity is called as recall. Specificity is known as the precision. Okay, specificity is known as the precision. And then the fourth one we are having is an F1 score. Okay, F1 score is nothing but it's a combination of precision and recall. Okay, remember the mean, harmonic mean, progressive mean. So harmonic mean. Okay, in the F1 score we'll be having the harmonic mean of precision and recall. Okay, harmonic mean of precision and recall will be having in the F1 score. So I'll just say the formulas also over here. Actually, I'm having an image over here. Yeah. Just refer to this image once. Just refer to the image once. It's how you see the confusion matrix table. Okay. If you're considering the predicted values over here, you're considering the predicted values and actual values in this way. So you'll be getting the sensitivity, specificity, precision, accuracy, the negative value prediction. Negative value prediction is again almost the same. Okay. Here, accuracy, precision, recall, F1 score. Now, let's say what exactly the formulas are. Okay. So in accuracy, the formula, let me just show you here. Yeah. Accuracy, the formula is true positive plus true negative by true positive plus true negative plus false positive plus false negative. What is this true positive plus true negative? How many true positive values are present plus how many true negative values are present in the combination of those values by all the values. Okay, true positive, true negative, false positive, and false negative. Okay, so in a similar way we are having this precision. Precision is true positive plus false positive. Okay, so in the precision we'll be considering only the proportion of the true positives among all the positives. Okay, true positives among all the positives we'll be considering. So it is true positive by true positive plus all the false positive. All the positive proportions we'll be considering for the predictions in the precision. Okay, and in the recall, where is recall here? Recall is also called as sensitivity, right? Recall is also called as sensitivity. So sensitivity means here what it is saying, proportion of true positives among all the actual positive instances. Okay, among all the actual positive instances. What is false negative here? It is actually false and it is also being predicted as false only. Correct. Fn. True positive means it is actually true and being predicted as true by TP plus Fn. TP is again the same. Fn is nothing but it is actually negative and it is also being predicted as negative only. So in that case, it will be proportion of true positive among all the actual positive instances. Okay, all the positive actual instances, all the positive instances. But in precision, what we are saying, all the positive predictions. Okay, true positives among all the positive predictions we are saying in prediction. I mean in the precision. Here we are saying all the actual positive instances. Okay, that is the main difference between this precision and the recall. Okay, precision, recall we can say it as sensitivity, or else yeah, there is this another formula for specificity also we can consider. We can consider precision for specificity, or else we can consider there is another formula for specificity also, where we'll be having this true negative by true negative plus false positive. We'll be considering all the true negative among all the negative predictions, right? True negative plus false positive. A slight change if you see the difference between sensitivity and specificity. There's a slight difference. Here in the sensitivity, what we are doing, it's a proportion of true positives among all the actual positive instances. Correct. Here what it is a proportion of all the true negatives, right? True negatives among all the what among all the actual negative instances. Correct. Among all the actual negative instances, it is false and it is also being predicted as false only, so it is false positive. So that is the difference between sensitivity and specificity. And recall can be called as sensitivity. Okay, recall can be called as sensitivity. Okay, fine. If you want to be very specific and if you want to consider only to calculate among all the positive, okay, among all the specificity, right? Specificity is negative instances, right? Sensitivity is all the positive instances, right? So specificity will be negative instances. If you want to calculate only the negative instances in that case, then we'll be going for the specificity. Okay, then we'll be going for specificity. If not, if you want to be precise, in the prediction, what we'll be doing, all the positive predictions only we'll be doing. So that is the main difference between precision and recall. This is recall. Okay, this is recall and this is specificity. Okay, and F1 score is remaining. F1 score is nothing but again it will be 2. The formula is 2 cross precision into recall by precision plus recall. Okay, so this is what the formula for F1 score is. Okay, F1 score is nothing but the harmonic mean of the precision and recall. For only the precision and the recall, you'll be calculating the mean, and for those values, you'll be, this is the formula. F1 score, the harmonic mean. Remember the harmonic mean for precision and recall. So the formula is 2 cross precision into recall by precision plus recall. Okay. So these are all the formulas, and also to do the classification metrics, to calculate only the specific part, or else the precision, or else the sensitivity, or the recall, the accuracy. Okay. To calculate all these. Okay. So when to use accuracy, when to use precision, when to use recall, when to be very specific, it all depends on the type of the problem that we're trying to solve. Okay, it all depends on the type of the problem that we're trying to resolve. Okay, is that clear, guys? Okay, now I'm having a small doubt. Okay, now I'm having a small doubt. Can you people clarify the doubt? Can you people clarify me the doubt? Okay, fine, fine. Yeah, yeah. Please try. Okay, when do we need to use accuracy? Let me know. When we will use accuracy, when we will use precision, when we will use this recall, okay, when we will use F1 score. So I'll just repeat this. Use accuracy in machine learning when the data set is balanced and the classes are equally important. Yes, good one, Jagdish. Good one. When the classes are all balanced, and all the classes are equally important, we'll be using this accuracy. Then when we'll be using this precision. Okay, you people know regarding these things in that case. Good one, Kishore. Okay. Yeah, I got the answer from Kishore. Thank you. And coming into recall and specificity. So I hope you people know. It's fine then. Okay, please remember when to use that. When to use what? Okay, when to use what? Do remember when to use accuracy, when to use recall, when to use precision, when to use specificity. Okay. No, F1 score, like when we need a balanced measure of the precision and recall. Okay, precision and recall, and yeah, when the classes are imbalanced. Correct. Yeah, when the classes are completely imbalanced, when we need a balanced score, we'll go for this F1 score. Okay, fine. Okay, this is it, guys. This is it. Just give me a minute. So I have just created a poll. Let me know. Okay, I have just created a poll. Let me know. Thank you, guys. Very good. So in that case, I think you people know already these machine learning algorithms, right? Everyone. Okay. I could have finished this in a much better manner, right? In that case. What about deep learning algorithms? Okay. What about deep learning algorithms, guys? No. Okay, okay, fine, fine. So you people are good with machine learning algorithms only, not with the deep learning, correct? Okay, okay, fine. So whatever the things which we are discussing in the session, I mean during the session, are you people able to recall the things? So please ask your doubt. Okay, okay, Kishore, we'll discuss about deep learning. Okay, don't worry. Okay, NASCAM portal you're asking. The NASCAM portal, it's like a center level portal. Okay, you'll be able to access all the courses. Okay, like be it related to skill development. Okay, all these courses will be up on the NASCAM portal. So you need to register in those courses. Okay, not to complete these programs, you need to register in those courses. If one no, fine. Okay, theoretically you are aware of machine learning and deep learning, but practically you're not. So when we are doing this linear regression implementation, did you people understand how exactly we are doing that practical implementation? Yeah, until now we have implemented only two things: linear regression and the logistic regression. By tomorrow we will complete this unsupervised learning. Okay, unsupervised learning will complete, and then on Friday we'll do complete implementation for the decision tree, random forest, ADA boost. Okay, KNN, all these algorithms we will implement. Okay. Okay, fine. It's 4:30 officially. You people may leave. Thanks for joining the session. Okay. Thank you. Thanks, everyone. Which link you're asking? Okay. Fine. Thank you. Thank you, Kishore. Thank you, guys. Thank you, Ashwini. Thank you, Jagdish. Thank you, Sai. Yeah. Thank you. Thank you, Nandini. Thank you, Narla. Thank you. You may leave the session, guys. Thank you, Rao. Thank you, Vijay. Thank you. Which link you're asking about? I'm not getting. Yeah. We'll be providing that link. Okay, just a minute. Yeah, thank you. Thank you, Satish. Thank you, Gayatri. Just give me a minute. We'll provide all those registration links. Okay. In the chat, we'll be updating the registration links, and also in the Telegram group also we have updated. Okay, please check. Yeah. Thank you. Okay, guys, I'm ending the session. Okay. Thanks for joining.